Hi guys, this is Dr. G here, and in this particular video we will continue our discussion on alkanes. And of course, in previous videos I have started discussing about alkanes and how to name simple straight chain alkanes, right? So in this video we will basically talk about uh, alkanes that are a little bit complicated, mainly because these alkanes are not going to be straight chain. They are going to have some small branches coming out of the main chain, so we call them branch chain alkanes, or we say that they are alkanes with substituents. Okay, so we will talk about the alkanes with substituents, and more importantly this video will discuss about a concept called isomers. Okay, so if you want to learn about isomers, or at least the uh, introduction and the first few information about some of the very important types of isomers, this video will really help you. Okay, all right, let's get to it. Here's the thing. Up until now, we talked about alkanes, and we know that alkanes are hydrocarbons. They only have carbons and hydrogens. They only have carbons and hydrogens. And alkanes, we learned straight chain alkanes up to now. So that means, alkane carbons are connected to no more than two other carbons. Either carbons are connected to one other carbon or two other carbons. Okay, no more than two carbons. So we call them straight chain carbons. And we also talked about cyclic alkanes. We also talked about cycloalkanes, right? So that is what we learned in previous lessons. But in here, we will talk about alkanes with branches, or in other words, alkanes that have substituents. Okay, so when you have more than three carbons, okay, so ethane, methane, and propane. Methane, ethane, and propane does not come into the discussion. Is not relevant to this discussion. Whenever you have uh, four and up, number of carbons that are more than four. I mean four and up. Okay, more than three actually. Okay, you can have different uh, types of alkanes. Okay, or you can have two different alkanes with the same number of carbons. Okay, so let's take a small example given in this slide. Here you have butane. Here you have butane. What is butane? Butane has four carbons, right? But means four carbons, right? So it has four carbons, and butane could be written in two different ways. Okay, butane could be written in two different ways. You can attach the four carbons. You can attach the four carbons straight. Okay, so this is the straight chain alkane. Okay, this is the straight chain. Okay, by the way, this is the same as, let's say, CH3, CH2, CH2, and CH3. Okay, both these are the same thing. Okay, they are the same thing. Why? Because all four carbons are connected uh, to not more than two other carbons. Okay, so you can bend it. I mean, you can write this in many different ways, but it is still a straight chain alkane. Okay, it is still a straight chain alkane. I mean, sometimes you might write it like this. Okay, CH3, let's say CH2, CH2, CH3. This is once again the same as this. Okay, same as this. So all these are straight chain alkanes. Okay, but let's say someone might write it like the way that I have given in the second structure. Okay, in here you might notice that there is a carbon. There is a carbon in this structure right here in the middle. This carbon actually has three other carbons attached. One, two, three. This middle carbon is attached to three other carbons. Okay, we didn't see that before. Okay, so whenever you have a carbon, okay, it could be one or more carbons connected to three or four other carbons. Okay, you know that carbon can form four bonds, right? So out of these four bonds, this carbon should be connected to at least three other carbons. Okay, at least three other carbons. Okay, so that means three or four carbons. We say that those compounds are branched chain alkanes. We say that those compounds are branched chain alkanes. Why did I say it is a branch chain alkane? Here is your primary alkane chain. Okay, this is your primary chain, and then this CH3 is a branch that is attached to that chain, right? But in here you never saw that. You saw that all four carbons connected in a straight chain manner, right? The first carbon is connected to the second one, second is connected to the third one, third is connected to the fourth one. Okay, so this is a straight chain. Okay, all carbons are connected to one another in a organized manner, but in here these three carbons are connected in a chain, and then CH3, this CH3 right here is coming out of the middle carbon. So now this CH3 on top, that is not a part of this main chain. We call it the primary chain. So anything that is not a part of the continuous primary chain, we call it a branch. Okay, we call it a branch, or we call it a substituent. Okay, we call it a branch, or we call it a substituent. Okay, we call it a substituent. So here's the thing, I mean, it might change the way that you look at it. Okay, you might consider that, okay, this is your primary chain, this could be your primary chain. Why? Because they are connected in a straight chain manner, right? So this is a continuous chain. The keyword is continuous. Okay, find a continuous carbon chain. Anything that is not included in that continuous chain, like this CH3 group, that is a branch, or we call it a substituent. Okay, and these two compounds, the straight chain one and the branch chain one, they are not identical. They are of course not identical. They have the same number of carbons because they both have 4 carbons and they both have 10 hydrogens. So they basically have the same chemical formula. Okay, they basically have the same chemical formula, but they both differ in the way they are arranged. Okay, they differ in the way they are arranged. In the first one, all 4 carbons are connected in a continuous manner. Okay, all 4 carbons are connected in a continuous manner. So this is a straightly this is continuous in a straight chain. But in here, these 3 are continuous and this is an outsider. Okay, or you can say these 3 are continuous and this is an outsider. So it doesn't matter how you dice it, you will still see that in the second structure you have 3 carbon chain that is continuous, and then you will have a CH3 group that is not a part of that continuous chain. So that CH3 group is known as a branch or an alkane. And the 2 carbon structures that you see here, even though they have the same chemical formula, they are different in the way the atoms are arranged, right? So therefore we call them isomers. We call them isomers. Okay, so if someone asks you what are isomers, isomers are chemical compounds. Okay, isomers are chemical compounds that have the same chemical formula, but they differ in the way the atoms are arranged. Okay, all right. So in this slide, I think I actually skipped this slide in my discussion, but I mean, this is basically the same stuff that we discussed in previous videos. Okay, we already talked about the general chemical formula for alkanes. Okay, and we learned the term saturated. So if you don't remember these details, you can of course go through this slide. Okay, but now we came to a new technical word. We call it isomers. Okay, so isomers are basically identical in chemical formula. They have the same number of and the kind of atoms, but they change in the way the atoms are arranged. Okay, they change in the way the atoms are arranged. But of course, to have isomers, you have to have at least, when it comes to alkanes, okay, when it comes to alkanes, you have to have at least 4 carbons to show isomers. Methane, ethane, and propane. Okay, you can write these 3 compounds in many different ways, but they are going to be identical. Okay, so methane, ethane, and propane is not going to have isomers. Okay, and if you take a look at butane, the one that we just discussed, it had a straight chain alkane. It had a straight chain alkane where all four carbons are in a continuous chain. Or you can have three carbons in a continuous chain and then one carbon as a branch, right? So these are the two isomers. Here is the butane, and here is the other compound with three carbons in a straight chain and then one carbon coming out as a branch. Okay, so these are the two isomers. But for pentane you can have a few more. Okay, for pentane you can have actually three more isomers. Okay, so these isomers are actually either straight chain. You can have one straight chain and then the rest will be branched chain alkanes. Okay, what are branched chain alkanes? Once again, they have carbons, okay, or one or more carbons with which are connected to three or more other carbon atoms. All right, so let's take an example. Okay, let's take an example. Let's take hexane. Okay, so I really want you to pay attention here. Okay, so let's take hexane, which means it has 6 carbons, and then how many hydrogens will you expect? 14 hydrogens, right? So in the exam I might ask you, draw all the possible isomers for hexane. Okay, the question is, draw all the isomers for hexane C6H14. Okay, this will be a nice question. So what are isomers? Isomers basically have the same chemical formula, but the atoms are connected differently. The atoms are connected differently. Okay, so this is a nice question that you could get in the exam. And now we are going to learn how to answer a question of this type. Okay, to do that we need to understand the term called isomer in more detail. So what I'm going to do now is I'm going to define this isomer term in more detail, and then we will come back and take a look at this same exact question. Okay, all right, so isomers or isomerism has many different areas. Okay, so as I mentioned earlier, isomers have the same chemical formula but different arrangement of atoms. Okay, so these isomers are of two different kinds. There are two primary kinds of isomers. Okay, or you can primarily categorize isomers into two major categories. Okay, the first category is called constitutional isomers. Okay, constitutional isomers, sometimes people call it structural. Okay, it is the same thing. Okay, don't get confused. Okay, so the first type of isomers are known as structural isomers. They are the easiest ones, to be honest, because their structure is different. Okay, and the second kind is called stereoisomers. We will also talk about all these stereoisomers in this class. Okay, but stereoisomers are very unique. Basically, atoms are in stereoisomers, atoms are oriented differently in 3D space. Okay, so when considering stereoisomers, we have to think about the shape of the molecule. Okay, the shape of the molecule, and then when you put atoms in 3D space, you will realize that even though the molecule looks similar in structure, the way the atoms are arranged in space is going to be different. So those isomers are known as stereoisomers. Okay, and we are going to talk about stereoisomers in much more detail in later chapters. Okay, and stereoisomers of course are going to be two kinds, geometric and optical. We will talk about these stereoisomers in much more detail later on. Okay, and then the structural isomers are the isomers that I'm more interested in at this chapter, because when it comes to hydrocarbons, structural isomers are the ones that are more important, especially alkanes. When it comes to alkanes, structural isomers are going to be more important. Okay, so once again, structural isomers have the same chemical formula, but atoms are connected differently. So you can easily, when someone give you two different structures, you can easily say that they are different by looking at the structure, because their atoms are connected differently. And there are three kinds of constitutional isomers. Okay, first kind is known as skeletal isomers. This is the most important one when it comes to alkanes. Okay, this is very important for alkanes. Okay, this is very important for alkanes. And then the second kind is known as functional group. Okay, functional group isomers. Okay, briefly talking about functional groups. Okay, functional groups are group of atoms that you see in organic chemistry, and these group of atoms usually behave similarly. Okay, behave similarly. Things like alcohol. Okay, alcohol has the functional group called OH. Okay, and if you take another functional group, let's say aldehyde has a functional group called COH. Okay, and you have something else in the other bond. R is anything else. Okay, so these are functional groups. This OH group or this aldehyde group, they are called functional groups. Why? Because they are a group of atoms that basically gives functionality to the organic molecule. Or in other words, these group of atoms introduce new chemical reactions or physical properties or chemical properties to the group of organic compounds. And these physical and chemical properties are going to be unique to each functional group. So the thing about alkanes is that alkanes do not have functional groups. Okay, carbon-carbon single bonds are going to be in every organic compound, almost every organic compound. So basically, alkanes are not considered to be functional groups. Okay, in fact, alkanes are the only organic compounds without a functional group. Okay, so basically alkanes have the generic stuff, the things that every other compound has. Things like, carbon-carbon single bonds, so carbon-hydrogen single bonds. Every other organic compound is going to have that, so there is no uniqueness to it. So alkanes do not have a functional group. And the third kind, the functional group isomers are actually based on the functional group. Okay, so if you have two different functional groups with the same chemical formula, then those are going to be functional group isomers. We will talk about it in more detail in the next slide. Okay, and position isomers are also not relevant for alkanes. Okay, if you have a functional group like alkenes have a functional group. Carbon-carbon double bond is a functional group. Okay, so depending on the position of the functional group, these isomers differ from one another. Okay, so the second kind is the type of functional group the chemical compound has. The third kind of isomers are called position isomers, or in other words, based on the position of the isomer, they are different. Okay, so these are the three kind of isomers that we are going to discuss in a second. Okay, but of course in a later chapter we will talk about all these isomers in more detail. Okay, in more detail. All right, so let's get to it. Let's start discussing more about constitutional isomers. Once again, guys, when it comes to alkanes, the only important constitutional isomer is going to be the skeletal isomer. This is the only important isomer for alkanes. Why? Because the other two isomers, the functional group and the position isomer, these two are not relevant to alkanes because alkanes don't have a functional group. Okay, all right, so let's take a look at the skeletal isomers. Let's take a look at the skeletal isomers. Okay, skeletal isomer means you have the same chemical formula, but the skeletal structure or the skeleton of the compound is different. Let's take the same molecule that we talked about in the last few minutes, butane. Okay, you can have 4 carbons in butane in a straight chain manner, where all 4 carbons form a continuous, key is continuous, okay, continuous chain. Okay, this is one way. Or you can have 3 carbons in a continuous chain and then one coming out of the middle carbon. Okay, one coming out of the middle carbon. So that is the other isomer. Okay, so these basically have the same chemical formula, but their skeleton is different, or in other words, their atoms are arranged in a different skeleton. Okay, the butane basically has 4 carbons in a straight chain, and then in isobutane, or this other kind, we will talk about the nomenclature in a later video. You have 3 carbons in a continuous chain, and then the 4th carbon comes out from the 2nd carbon. Alright, so how about this one? Is this another skeletal isomer for butane? I mean, this is butane right here. This is butane. Is this a different skeletal isomer? The answer is no. Why it is no? Because as you can see, all 4 carbons are still in a continuous chain. So the skeletal structure is basically identical to this one. Okay, identical to butane. I mean, doesn't matter whether you drew it in a different arrangement, still these two are going to be identical. Why? Because all 4 carbons are in a continuous chain. Okay, continuous chain. See, 1, 2, 3, 4, 1, 2, 3, 4. They are all in a continuous chain, so they are identical. Okay, they are identical. All right, so that is skeletal isomers. Okay, and then an example for functional group isomers is ethanol and dimethyl ether. Okay, so in other words, alcohol, ethanol is an alcohol, so alcohol and ether. Alcohol and ether are like cousins, okay, or actually they are isomers, so you can consider them as cousins. Okay, they have the same chemical formula. So if you count the number of carbons and hydrogens here, it will be C2H6O, and if you count the carbons, hydrogens and oxygens, it will be C2H6O. So both these compounds essentially have the same chemical formula. But of course, alcohols have a OH. Alcohols have what? An OH. Ethers have a sandwiched oxygen. Ether has a sandwiched oxygen. So basically you have oxygen sandwiched between 2 other carbons. Okay, so these are called ethers. Okay, alcohols have an OH. Okay, ethers have an oxygen just like in alcohols, but this oxygen is sandwiched between 2 carbons. Okay, so those compounds are known as ethers. Okay, so ethers and alcohols, even though they share the same chemical formula, they don't have the same functional group. Alcohol has the OH, ether has the sandwiched oxygen. Since they have 2 different functional groups and still share the same chemical formula, we say that they are functional group isomers. We say that they are functional group isomers. Okay, and the last kind is known as position isomers, or position of the functional group isomers. Okay, so basically in here what happens is that you have the same number of carbons, hydrogens, and whatever the other atoms that you have. So the chemical formula is identical. Okay, but the position of the functional group is going to be different. Okay, so in the left hand side molecule, the NH2 group is on the 2nd carbon, right? The NH2 group, which is the functional group here, it is on the 2nd carbon. But in this right hand side molecule, which is propylamine, okay, the functional group is on the 1st carbon. So 2 versus 1. Definitely the functional group is in a different carbon, so the position is different, right? So we call them position isomers. Okay, so let's get to our I think there is a study check here in the next slide. We will do that, and then we will go to the notepad. Okay, and once again guys, we are more interested in structural isomers in hydrocarbon chapter. Okay, and when it comes to structural isomers, okay, there are three kinds. Skeletal isomers, functional group isomers, and then position isomers. But for alkanes, which means there is no carbon-carbon double bonds or any other atoms other than carbon and hydrogen, the only isomer that matters is called skeletal isomers. Okay, which means you try to arrange carbons in different chains. Okay, you can of course have one straight chain, alkane, and then the other isomers will have a branch or more branches depending on the formula. Okay, so what I want you to do is I want you to try this study check. Okay, and then see if you could get the answer that is going to be identical to mine. Okay, so in here I want you to draw three possible structural isomers of pentane. I want you to draw three possible structural isomers of pentane. Okay, pause the video and try it. All right, so for pentane, you have 5 carbons. Okay, you have 5 carbons. So from here onwards, I highly recommend that you guys work in skeletal structures, okay, which is the easiest to draw, okay. And then the easiest isomer that you can draw for 5 carbons is what? The straight chain one. Put all 5 carbons straight. 1, 2, 3, 4, 5. Get it? So that is one isomer, the easiest one, the straight chain one. If you are not very comfortable in, skeletal isomers yet, you can draw it like this: CH3, CH2, 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 CH3. But of course, here's the thing: when you are using condensed structures like this one, the chance of getting things wrong are more. Why? Because your hydrogens has to be accurate and all those things. Okay, but when you are drawing the skeletal structure, you simply have to what? You simply have to count the ends and bends. See, 1, 2, 3, 4, 5. Draw a zigzag by counting the carbons, right? So every end and a bend is going to be a carbon, right? So 1, 2, 3, 4, 5. Okay, so that is your first isomer. Very straightforward. And this is also the straight chain one. This is the straight chain one. Okay, but you can only have one straight chain one. Okay, don't be the guy who's going to ask that, hey, can I have something like this? 1, 2, 3, 4, 5. This is different. This looks different. No, this is not different. Okay, this is still the straight chain one that you draw before. Okay, how do I know that? Because you have all 5 carbons in a straight chain. Okay, 1, 2, 3, 4, 5. They're all in a straight chain. Okay, see, 1, 2, 3, 4, 5. So what is the difference? There is no difference. They are both straight chain ones, and all 5 carbons are connected to 1 or 2 carbons. Okay, so they are identical. So they are the same thing. Don't draw things like that. Okay. All right. So next, what I'm going to do is something very, very simple. Okay, I'm going to keep 4 carbons. I mean, I had 5, so I'm going to keep 4 carbons constant. Okay, so I'm going to keep this part constant. Okay, and then I'm going to break 1 carbon. Okay, I'm going to break this carbon and then put it somewhere else. Okay, I'm going to break that carbon and put it somewhere else. Okay, let's do it. So once again, I'm going to keep 4 carbons constant. 1, 2, 3, 4. These 4 are going to be constant. Okay, nothing is different. These 4 are going to be constant. 1, 2, 3, 4. 1, 2, 3, 4. Nothing happened to those 4. What I'm going to do is I'm going to take this carbon and then put it on some other carbon. Now it is on the 4th carbon, right? I'm going to put it on 3rd carbon. I'm going to put it on 3rd carbon. Right here. Okay. So that will be a different isomer. So you put it on the 3rd carbon. Okay. So if you want to draw the condensed structure, okay, since we are still learning, okay, see if you could draw the condensed structure, or maybe some people might prefer drawing the condensed structure. Okay, so this carbon right here, This carbon right here is CH3. Why it is CH3? Because that carbon only has one carbon-carbon bond. You need 4 bonds, you only have 1. Okay, so 4 minus 1 is what? 3. So you have 3 hydrogens. Go to the next carbon, which is this one. Okay, it has 2 carbon-carbon bonds. You have 2 carbon-carbon bonds. So you need 2 hydrogens, right? 4 minus 2 is 2. So CH2. Okay, go to the next carbon. Okay, here is that next carbon. This carbon has 3 carbon-carbon bonds. Okay, it has 3 carbon-carbon bonds. Okay, so 4 minus 3 is what? 1. So you only need 1 hydrogen. You only need 1 hydrogen. And then this carbon right here already has 1 carbon-carbon bond, so it needs 3 hydrogens. This carbon has 1 carbon-carbon bond, so it needs 3 hydrogens. Okay, so this is the condensed structure. They are different from one another. Why? Because in here you have all 5 carbons in a straight chain. It's a continuous chain. In here you have a continuous chain of 4 carbons. If you have a continuous chain of 4 carbons, and you have one other carbon coming out of the third carbon. Okay, so that is different. You have a continuous chain of 4 carbons instead of a continuous chain of 5 carbons. So definitely they are different. Definitely they are different. Okay, so what could we do next? Okay, so what I did before was I took this methyl group, or the CH3, or this CH3 group, and I put it on the next carbon, right? Can I put it in here? That is also different. So let's try that. Let's try that. Okay, so you have 1, 2, 3, 4 carbons, and then here's the CH3 group. But here's the thing, these two are identical. Why? Because let's say you have 1, 2, 3, 4 carbons. In here you have 1, 2, 3, 4 carbons, and then a CH3 group is coming out of the second carbon. Don't say it is the third carbon, okay, because you have to number it similarly. Okay, so you start numbering from the end close to this branch, and then you realize that in both occasions the carbon right here with 3 other carbons connected, it is the second carbon. So they are identical. So there is no point of moving it into the third carbon, right? There is no point of moving it into third carbon. So what I'm going to do next is that I'm going to keep this part constant. I'm going to keep this part constant. Okay, and then I'm going to break this and then put it in this carbon. Put it in this carbon. Okay, so let's do it. So you have, oh, excuse me. All right, so you have a 3 carbon chain, continuous 3 carbon chain. Okay, not 4, not 5. So if it is a 4 or 5, it could be identical. Okay, so it has a 3 carbon continuous chain, and then here's that CH3 group right here, and then here's the new one. Okay, this is the new one. So if you want to draw the condensed structure, start with any carbon. Let's do this one. So it will be CH3. Go to this carbon, it will be a C, and then it will have a CH3 to the bottom, CH3 to this side, and then of course it will have a CH3 right here. Okay, all right, so these are the 3 structures that you can have. These are the 3 structures that you can have. Okay, or isomers that you can have. I think I gave you an example in a different sheet of paper. Okay, draw all the isomers for C6H14. Okay, so now you should be able to do it. So pause the video and see if you could get the same answer that I'm going to get. Okay, all right, I'm going to start with all 6 carbons straight, or continuous chain of 6 carbons. 1, 2, 3, 4, 5, 6. Don't be ashamed to count your carbons in your head. Okay, that is how you learn. You just need 6 carbons, right? So 1, 2, 3, 4, 5, 6. Good. I have the straight chain isomer. This is my first isomer. And second, what I'm going to do is I'm going to break this CH3 group, and then put it some other carbon, maybe this one. Okay, I will put it somewhere else. All right, let's try this. Let me go back to my pen. All right, so break that, so you will only have 5 carbons. 1, 2, 3, 4, 5 carbons, and then the CH3 group is going to be here. Here's my second structure. Okay, now what you can do is move the same CH3 group to the next carbon. Move this to next carbon. It will be different because this is not symmetric. Okay, this second isomer is not symmetric. So if you do that, what you're going to have is something like this. You have the same 5 carbons straight. So 1, 2, 3, 4, 5, and then the CH3 group will be here. Okay, this is the third isomer. All right, so you can try to move it to the other carbon. Okay, you can try to move this to this carbon, but here's the problem. If you do that, you will end up with the same thing right here. Okay, because you will have a CH3 group on the second carbon. Okay, it is the same as that, so don't move it anymore. Okay, don't move it anymore. All right, so how do we get some new ones? Okay, so let me change the color of my pen. All right, so now we have 2 structures. Okay, we have one structure which has 6 carbons straight. We have 2 structures, structure 2 and structure 3, with 5 carbon continuous chain. And then we cannot have any more 5 carbon continuous chains, but we can have a 4 carbon continuous chain. 1, 2, 3, 4 carbon continuous chain. Okay, which means I have to have 2 other carbons, right? So I can put one here and the other one here, right? So in here, I mean, if you are confused, if you feel like you're confused, let me show you what I do. Okay, in the first one, I have all 6 carbons in a continuous manner. In my second and third structure, I only have I tend to number my continuous carbon chain close to the branches. Okay, there's a reason for that. You will learn it later when we learn about nomenclature. Okay, but I mean, I tend to number it starting from the end closest to a branch. Okay, and then that has 5 carbons in a continuous chain. And here again 5 carbons in a continuous chain, but 2 and 3 are different. Why? Because in the second structure the branch is coming out of what? Out of the second carbon, but in here the branch is coming out of the third carbon. Fourth structure is different. Why? Because I have only 4 carbon continuous chain of carbons of only 4. Okay, so I only have a 4 carbon continuous chain. Okay, and then I have to have 2 other carbons, right? So I put one here. Okay, this is my 5th carbon and this is my 6th carbon. Okay, and then I can draw a very similar structure to 4th one. Okay, with 4 carbons, but what I'm going to do now is that I'm going to break this CH3 group and then put it in the next one. Okay, because now the branches are coming out of second and third carbon, but if I put the 2 branches on the same carbon, it will be something like this. Okay, look at this one. It has a continuous chain of 4 carbons, 1, 2, 3, 4, and here is the 5th and 6th carbon is coming out of the second carbon. All right, so that is another structure. That is another different structure. So I have drawn 5 different isomers for C6H14. Okay, C6H14. All right, so I hope you followed it. Okay, and quickly check whether you can draw some more, but I think this is all the isomers that we can draw for C5H10. Okay, these are all the isomers that we could draw for C5H10. I'm sorry, C6H14. C5H10 is actually cyclopentane. I mean, I misspoke. Okay, C6H14. All right, let's go back to our lecture. And now, the next slide, we are going to talk about substituents in more detail. Okay. First of all, I have a brief sentence or two about how to name these substituents. Okay. How to name these substituents. Okay. So basically, the substituents, especially the carbon chain substituents, okay, they end with YL. YL. Okay. So if you have a branch called CH3, okay, let's say you have a branch called CH3. What is the one carbon Greek prefix? Because this substituent only has one carbon, right? This branch only has one carbon. So one carbon is meth. Okay, the name of this will be methyl because you put YL to the end, right? To the end. Methyl. Okay. So sometimes you can have halo substituents, okay? Halo substituents. I mean, I might use some questions with halo substituents just to make things interesting. Okay, the thing about halogens, okay, halogens are basically fluorine, chlorine, bromine, iodine, okay, group 7A elements. Okay, fluoro, chloro, bromo, iodo. I mean, fluorine, chlorine, bromine, and iodine. These are very, very common substituents. Okay, why? Because they are very similar to hydrogen when it comes to bonding to carbons. Okay, so they will also form, let's call them X. They will also make a single bond and attach to carbons. Okay, just like hydrogens, right? Hydrogens also made a single bond to attach to carbons. So these guys will also commonly form a single bond and attach to carbons. Okay, so basically these halogens can easily substitute hydrogens. Okay, hydrogens. So when you are naming these halogens, okay, you call them fluoro for fluorine, chloro for chlorine, bromo for bromine, and iodo for iodine. Okay, that is how you name them. Here are some of the common substituents that you might want to know for your first exam and of course for the assignments. Okay, I mean, you can have many different and different types of substituents, but most common ones are methyl. Of course, methyl substituent or the branch has only one carbon. Ethyl has two carbons. Propyl once again have four, so butyl should have four carbons, right? Propyl has three, excuse me. So propyl has three carbons, and then of course butyl should have four carbons. Pentyl should have five carbons, like that. But I mean, most common substituents are going to be methyl, ethyl, propyl when it comes to alkyl substituents. And sometimes you can have a three carbon substituent just like propyl, but this substituent, if it is connecting from the middle carbon, okay, so propyl connects from the terminal carbon. Okay, so if this three carbon substituent is connecting to the main chain from the middle, we call it isopropyl. This is important to remember. Okay, this is important to remember because just because it has three carbons, we don't call it propyl. Okay, if the three carbon branch is connecting to the main chain from the middle carbon, we call it isopropyl. Okay, this is something that most people get wrong in the first few questions. Okay, all right, so if you have fluorines, chlorines, bromines, iodines, I mean, they will be halo. Okay, they will be halo depending on the halogen. Okay, it could be fluoro, chloro, bromo, or iodo. All right, so those are the names, and then let's get back to our writing pad, and then try to identify the substituents that we had. Okay, so in the first one, it's a straight chain one, so everything is in a continuous chain, so you don't have any substituents. In here, in the second and the third one, we have a methyl substituent, right? These are methyls. This is a methyl. This is what? A methyl. This one has two, methyl groups. Here is a one, here is a methyl. Here is the other methyl. In here also there were two methyl groups. Okay, so now we know how to identify substituents. Let's do a quick question. Okay, let's try to draw, practice these isomers a little bit more. Let me give you a formula and then see if you could draw all the isomers for it. Okay, so here's the question. Draw all the isomers for C4H9Cl. Okay, see if you could draw all the isomers for C4H9Cl. First of all, is this formula correct? Okay, if you have 4 carbons, you can have a maximum of how many hydrogens? 10 hydrogens, right? You can have a maximum of 10 hydrogens. But of course, one of the hydrogens was converted to a chlorine. Okay, one of the hydrogens were converted to a chlorine. Chlorines are very similar to hydrogens, so they can easily replace hydrogens. So that is why you have only 9 hydrogens. The 10th hydrogen was replaced by a chlorine. So this formula is correct. So we know that it is what? It is a organic compound with a chlorine attached. The first thing that you will do when drawing isomers, okay, you might want to pause the video and try and see if you could draw isomers. Okay, the first thing that you might want to do is to put all 4 carbons together, because it has 4 carbons, right? So put everything together in a straight chain. Start counting. 1, 2, 3, 4. There's your 4 carbons. Okay, and then put the chlorine at the end. Okay, this will be your first compound. Here is your first isomer. Okay, what I usually do next is that I will try to change the location. Of my functional group. Okay, so I will basically try to move it somewhere else. Okay, so chlorine is a unique thing. Okay, let's call it the functional group here. Okay, because it is different as compared to all the carbons and hydrogens here. So what I will do is I will try to move it to a different location. Okay, for now it is in number 1 carbon, right? It is in number 1 carbon. Oh, excuse me. So now for now it is in number 1 carbon. Okay, so let's move it to number 2 carbon. Okay, so we will draw the same skeleton with 4 carbons. 1, 2, 3, 4, and then the chlorine will be right here. Okay, chlorine will be right here. And let's number it. 1, 2, 3, 4. So try to number it close to this substituent, the chlorine. Okay, so it will always be number 2 here. Okay, and then you can try to move it to the 3rd carbon, but here's the thing: once you move it to 3rd carbon, it will be on the 2nd carbon when you renumber it. Okay, so there's no point of moving chlorine again. Okay, so these two are definitely correct because they are very different from one another. Of course, here's my 2nd structure. Can you draw something else? Can you try to draw something else? What you can try to do is that, once you are done moving the substituent or the unique thing, let's call it the functional group or the substituent for now, because we don't know the difference. We don't have to know the difference at this level. Okay, so we cannot move the functional group along these 4 carbons anymore. Okay, we cannot move the chlorine along this 4 carbon ring anymore. So there's no point of moving it. So we have to stick to these 2, but let's see if we could break a carbon somewhere and then put it somewhere else. Okay, so let's keep let's keep carbon number 3, 2 and 1. 1, 2, 3 the same. Okay, is your chlorine, but we are going to remove this fourth carbon and then put it on the third carbon. Sorry, it is already on the third carbon, so put it on the second carbon. Okay, so that should be different. That should be different. So let's number it. Here's our 1, 2, and 3 carbon. Initially, the fourth carbon was on the third carbon, but now it is on the second carbon. So this is different. This only has a continuous chain of 3 carbons. In the beginning, we had 4 carbons. Now you only have 3 carbons. And then the substituent, the methyl group is on what? On the second carbon. Okay, so this is different. This is different. This is a good thing. All right, so let's draw something from this one. Okay, from the second one. Okay, so in here we have a 4 carbon chain, and then we will break a carbon. Let's break the fourth carbon, and then let's put it on the second carbon. It is on the third carbon now. Let's put it on the second carbon. So don't change anything else. Okay, the 3 carbons should be identical. Okay, 1, 2, 3, and then the chlorine, nothing changed. We kept this part constant. Okay, and then the fourth carbon, we are going to put it on the second carbon. Okay, so if you number it, you will see the difference immediately. 1, 2, 3. So we only have a continuous carbon chain of 3 carbons. Initially we had a continuous chain of 4 carbons. Now we only have 3 carbons, and then here is our methyl group, right? Here is our methyl group. Okay, all right, so these 4 are the isomers that you can draw. Okay, all right, so in the next slide you're going to learn how to name organic compounds with substituents. Okay, in the next slide we are going to learn how to name organic compounds with substituents. So as you can see, these are some of the very common substituents we will find in here. But when naming organic compounds, so alkanes or organic compounds, what we should do first is that we have to find the parent carbon chain. Okay, we have to find the parent carbon chain. This is a very important thing, finding the parent carbon chain. When naming alkanes with substituents, the first thing that you will do is you will find the parent carbon chain. So what is the parent carbon chain? What is the parent carbon chain? The parent carbon chain is known as the longest continuous carbon chain. Okay, the longest continuous carbon chain is known as the parent. So the first thing that you will do when naming organic compounds is that you will identify the longest continuous carbon chain, and then you will name it. Okay, you will name it. Let's say it has 5 carbons. The name of the longest continuous carbon chain will be pentane. Okay, so you will write the name for the parent carbon chain just like a straight chain alkane. Okay, and then let's say you have substituents. Of course, we are trying to name a compound with substituents. Then what you do next is that you will number the parent chain. Okay, so first you figure out the parent chain and you name it, and then you number the parent chain. Okay, so then you number it. So numbering is unique. When you number, okay, any chain has 2 ends. Okay, any chain has 2 ends, but you should start numbering from the end closest to the substituent. Okay, so when you are numbering your chain, you should start from the end closest to a substituent. Okay, and then you will identify the substituents, and then you will number the substituents, and then finally, okay, you will give the location and the name for each substituent, and you put every substituent name in alphabetical order. Okay, so give the location and name for each substituent. So every substituent will have a name. Let's say it is methyl. It will also have a location. Okay, so depending on the carbon where it is present, it could be 3-methyl. Okay, but of course when you have a number next to a letter, you always separate them using a dash line. Okay, so this will be 3-methyl. Okay, and then that will be the name of the substituent. Okay, so every substituent should have a location as well as a name. Okay, and then if you have multiple if you have multiple substituents, you will worry about the alphabetical order and then put everything together as a one whole word. Okay, that will be the final name. All right, let's try to name this compound. Okay, let's try to do this study check. Okay, so in here, let's find the longest continuous chain. Okay, let's find the longest continuous chain, which is this one right here. Okay, this will be the longest continuous chain. Why? Because it has 5 carbons continuously. So that is your longest continuous chain. Once you have the parent, okay, you write the name of the parent. So it is pentane. And then identify the substituents. Okay, you have a substituent here, you have a substituent here. Okay, so once you have identified the substituent, then you have to number the parent. Okay, you have to number the parent. So this is our parent right here. If you don't remember, this is our parent. Let's number each carbon in the parent starting from the end closest to a substituent. So let's number it here: 1, 2, 3, 4, 5. Why didn't I start numbering from here? 1, 2, 3, 4, 5. Someone might have started from there. But as you can see, if you start from this side, if you do the blue method, the first substituent that you are going to find is on the 3rd carbon. But if you use the red method, the first substituent is going to be on what? The 2nd carbon. So of course, you have to start numbering from the end closest to your first substituent. Okay, so that is why we stick to the red method. Okay, so this is your method. Okay, so you have a substituent on the 2nd carbon and the 3rd carbon. The substituent on the 2nd carbon is chloro. Okay, and the location is 2, so it is 2-chloro. And then this one is a methyl, but it is on the 3rd carbon, right? So it will be 3-methyl. Okay, once you have the names and the locations of the substituents, put everything together according to alphabetical order. Okay, alphabetical order. So C comes before M. So the correct name will be what? Correct name will be 2-chloro 3-methyl pentane. Correct name will be 2-chloro 3-methyl pentane. Okay, 2-chloro 3-methyl pentane. Okay, that is how you do it. You put everything together. By the way, whenever you have a letter and a number, you always separate them using a dash line. Okay, what I want you to do is I want you to practice naming. Okay, so there will be a couple more examples. What you can do is you can actually try to name the compounds that you have here. Okay, I mean, I only have like 1 minute left in this video, so I don't think I have enough time to name all these compounds. But what I want you to do is I want you to draw these structures in a separate piece of paper and see if you could name them. Okay, so if you have any questions, please let me know. That will provide you a good practice on how to name these compounds. And of course, I will be publishing a separate video on naming alkanes. Okay, I want nomenclature is a very important part in organic chemistry, especially at this level. So I'm going to publish a separate video on naming alkanes. Okay, so I recommend that you guys also watch that video, and of course you can practice nomenclature by trying to name all these compounds. Once again, these are isomers. So therefore all these compounds should have different names. Okay, they will never have the same name twice. Okay, so all these compounds, all these 9 compounds should have different names. Okay, see if you could get them by yourself and let me know if you have any questions. Okay, you guys have a nice day. Have a good one.